Hello, my name is Scott Stephenson, and I'm a physical scientist at the RAND Corporation. I'm interested in the linkages between climate change and human activities, particularly in the Arctic, where warming is occurring at twice the rate of the global average. In this lecture, I will discuss some of the key implications of climate change in the Arctic, specifically how melting sea ice is enabling greater access to the Arctic Ocean. It's possible that as the Arctic Ocean transitions to a seasonally ice-free state, new shipping routes will emerge offering shorter pathways for global trade, new oil, gas, and mineral resources will be developed, and tourism and fisheries will expand northward. While it is true that reductions in sea ice will enable some economic opportunities as a result of longer navigation seasons, it's important to realize that whether those opportunities will be realized will depend as much or more on infrastructure, such as the availability of polar-class ships, as well as global economic trends. Furthermore, while the long-term trend toward an ice-free Arctic is clear, the timing of the transition to ice-free and the geographic distribution of changing access are still somewhat uncertain. So, the question of whether climate change will lead to an economic transformation of the Arctic is rather complex. It is undoubtedly true that Arctic sea ice is diminishing. Sea ice extent in September, the month when sea ice reaches its annual minimum, has been trending downward since satellite records of the Arctic began in 1979, with a record low in 2012. Examining mean extents by decade shows clear reductions from decade to decade in nearly every month since the 1980s. Last year's minimum effectively tied for the second lowest on record. Here you can see the difference between September 2019 and the median extent in September from 1981 to 2010, showing large areas of open water in the seas north of Alaska and eastern Russia that had previously been ice-covered year-round. These larger areas of open water mean that the Northern Sea route along Russia's coast and the Northwest Passage through the Canadian archipelago will have a greater chance of being open in a given year, and will be open for longer periods of time. The Northern Sea route typically opens first each year and is more robustly accessible than the Northwest Passage, which is often closed due to the import of thick ice into the Canadian Straits from the Central Arctic Ocean. In the summer, ships may navigate in the Arctic for numerous reasons, although the vast majority of Arctic voyages are destinational in nature. In these data from the Arctic Marine Shipping Assessment Report published in 2009, you can see the pathways taken by ships, mainly for resupplying communities, supporting oil and gas operations, fishing and tourism, with the occasional visit to the North Pole for scientific research. The Arctic Marine Shipping Assessment Report, or the AMSA report, was an important document that not only outlined the types of marine operations that typically take place in the Arctic, but it also set a framework for establishing safety and environmental standards for the region. Since the AMSA report, numerous other assessments of Arctic shipping have been released, such as this one from the U.S. Committee on the Marine Transportation System. Here, the colors represent the total distance traveled by ships through each cell in the Bering Strait region in 2017, showing a high concentration of shipping activity through the strait, in the waters near Prudhoe Bay, and around the Red Dog mine north of Kotzebue. These are primarily destinational voyages supporting mineral and oil extraction that likely would have happened in the absence of climate change, but reduced sea ice is making access to those sites easier and for longer periods. In addition to ongoing extractive activities, the Arctic holds large undiscovered oil and gas resources, as shown in these maps from the U.S. Geological Survey in 2008. Here, the darker colors represent larger estimated undiscovered reserves in the geologic regions of the Arctic. In total, the Arctic is estimated to hold approximately 13% of the world's remaining oil and 30% of the world's remaining gas, though much of this is onshore and of limited access by ship. Whether these resources are brought on stream mainly depends on the future global demand for such resources, as well as on changes in the supply of other more accessible resources around the world, because the environmental conditions of the Arctic make drilling there very expensive relative to lower latitudes. It is sometimes said that the discovery of oil and gas resources will ignite a scramble for territory in the Arctic, but a closer look at the zones of maritime control in the region reveals that this is unlikely. Here, you can see that the majority of the Arctic Ocean already falls within the 200 nautical mile boundaries of the exclusive economic zones of the Arctic states, namely the US, Canada, Norway, Russia, and Denmark through its autonomously governed territory of Greenland. There is an area of the Central Arctic Ocean that is currently claimed to various degrees by Russia, Canada, and Denmark, and this is being resolved peacefully via a mechanism defined by the United Nations Convention on the Law of the Sea, or UNCLOS. The US is unable to make such claims because it is not a party to UNCLOS, but if it were to join the treaty, it could theoretically make a claim to a region north of the Beaufort Sea. Given the various uncertainties surrounding the economic and political future of the Arctic, it's helpful to think of the region as a coupled natural and human system, wherein changes to the natural environment, such as sea ice melting, may impel changes in human activities, such as investment decisions leading to more shipping, which may then cause further changes to natural systems. While many of the physical mechanisms involved in this feedback loop are well understood, there remain large uncertainties in the realm of human decision-making and in the ways in which the resulting impacts will perturb the climate system. For example, it's possible that increased shipping in the Arctic may accelerate climate change further by depositing black carbon, or soot, on snow and ice, which lowers its albedo and increases its absorption of solar radiation. It's also possible that sulfate aerosol emissions from ships may lead to increased cloud formation, which could reflect sunlight back to space and result in a cooling effect. Which of these processes will dominate will depend on where ships choose to navigate and on the type of fuel that ships use. Therefore, while the effect of some environmental impacts of shipping in the Arctic, such as oil spills, may be easy to predict, others are murkier and depend on policy decisions that have yet to fully play out. In any case, it is clear that infrastructure and polar-class ships will play an important role in the level of future access to the Arctic Ocean. Sea ice varies in thickness throughout the Arctic, and while the overall thickness of sea ice has declined in recent years, it remains a hazard to ships without ice strengthening. Furthermore, as the majority of the Arctic will be ice-covered in winter, even under severe climate warming scenarios, polar-class ships with ice strengthening will continue to be required for fall and winter operations. These three ship classes represent three levels of investment in ice operations, ranging from no ice strengthening in an open water vessel, up to a nuclear icebreaker that can withstand encounters with thick, multi-year ice. We can see how the choice between a polar-class vessel and an open water vessel is very important to understanding future Arctic marine accessibility. Here, the red lines represent the shortest possible routes through the Arctic in September using polar-class vessels, while the blue lines represent routes through the Arctic using open water vessels, as projected by an ensemble of climate models. Near the early 21st century, most of these routes approximate the Northern Sea route near the Russian coast. But by mid-century, we can see that, according to the climate models, polar-class vessels are able to sail directly over the North Pole in September, due to vastly diminished thickness and extent of sea ice in the Central Arctic Ocean. In contrast, open water vessels remain primarily confined to the coastal routes, and in practice may end up being escorted by icebreakers, as is currently required by Russian law. It is important to realize that these routes represent optimal access only and do not take into account other physical factors that can affect navigation, such as weather, nor do they suggest that the economics of shipping in this relatively hazardous environment will make such routes viable. In summary, the confluence of physical and human factors in the Arctic point to a complex future for marine access. Given the uncertainties inherent in the global economic system, it may be more appropriate to think of climate change as an enabler rather than a driver of future marine operations in the Arctic. We can also expect that regulatory decisions, such as whether to ban heavy fuel oil, establish marine protected areas, and require icebreaker escort, will profoundly shape the picture of human activity in the Arctic in the years to come.